We just added water. That's it. That's why it's called a hydrate. Okay. The one thing that we said was a mistake in that last step should have been split into two steps. We should be removing the hydrogen and then adding the hydrogen. Students are tempted to go through and do something like an intramolecular protonation, deprotonation with those purple arrows. Notice the color coding, right? We're doing it at the same time. You should not do that. For what reason? Too far would actually facilitate the reaction. What we're looking at is 1, 2, 3, 4 atoms in the transition state to allow this to occur, which means we're effectively forming a cyclobutane. Are cyclobutenes stable? No. And why not? Because of the angle strain. There's no way that we'll be able to get those 4 atoms aligned to be able to do the transfer of electrons intramolecularly. So we have to go external. And yes, that sucks from a mechanism point of view or a mechanism drawing point of view because you have to draw 2 mechanistic steps where a species comes in, removes 1 hydrogen, and a species comes in and dumps another hydrogen back on the structure. So it has to be split into 2 steps. Okay? So it is bad to do the intramolecular transfer. Okay? When is it okay to do an intramolecular transfer? Four atoms is bad. 3 atoms is bad. 5 atoms is okay. And 6 is absolutely acceptable. Okay? So only under those circumstances would we expect to see an intramolecular transfer. Okay? It is very, very rare to occur. So we shouldn't be showing that. So in this case, all we did was just throw water in with our ketone. Okay? If we evaluate water, would we expect that to be a strong or a weak nucleophile? It's weak because it's not charged. Why else might it be considered weak? What can you tell me about oxygen?
Can we form 2 bonds?
No, it can form 3 bonds, H3O+. Say oxygen in comparison to carbon, or nitrogen, or hydrogen.
It's more electronegative.
Oxygen is more electronegative. Being more electronegative, is it willing to give up its electrons? No. So oxygen is generally considered a weak electrolyte, or weak nucleophile. Okay. Could we improve the rate of the reaction? Okay. Well, yeah. We could improve the rate of all reactions by doing one of 2 things. What is one of those things to speed a reaction? Or one or both of 2 things? So we could add heat, fair enough, one of 4 things. Okay, we could change the acidity or basicity of it. Okay, I would argue that that's a secondary feature on how we're doing this. So you're right, making it acidic or basic can help, but how is it helping? We could make the carbonyl carbon more electrophilic. Okay? It needs to become more positive. When we ran this reaction, we're really based off of 2 things. That electrophilic carbon and that nucleophilic oxygen. If that partial positive was more positive, this reaction would go faster. If that partial negative was more negative, it would go faster. What happens if you say add an acid? If we add an acid, we need to neutralize that acid. Well, what's the most reactive thing in solution? Probably the pi bond. That pi bond can react with the hydrogen leaving behind a formal carbocation. We now have a stronger electrophile. Okay? What if we'd added base? What is that base going to do? It'll remove the hydrogen from our water, leaving behind a formal negative. We've made the nucleophile more nucleophilic. So we can change the acid or base conditions of our reaction to speed it in some form or another. And with that, Here you go. Make that nucleophile more nucleophilic and draw out your mechanistic procedure. One of the things that we could evaluate would be, number one, what is our nucleophile, what is our electrophile? So this is why we drew out the reaction to begin with, where we showed water attack the carbonyl. Okay, that was our previous system. Well, if water is doing the attacking, it is the nucleophile. The carbonyl is the electrophile. Okay? So we drew that out, and then we also need to remember that carbonyls are by and far electrophiles. Okay? That should be kind of stuck in your brain, that when you see a carbonyl, it should be acting as an electrophile. It is not easy to make them nucleophiles. Okay? So if that's the case, I need to make water more nucleophilic. To do so, it needs to become more negative. Well, the way it can become more negative is if we add a base that can remove one of those hydrogens. Okay, the result is that I would end up, and I'm going to draw it down below, end up with hydroxide with a formal negative. Our nucleophile is now more nucleophilic because it's negatively charged. We didn't do anything to our electrophile, so that would still be there. Now what can happen? Have the nucleophile attack. We'd have our negative now on that oxygen. We have our new bond to our OH. How do we stabilize that negative charge? We can protonate, likely using water from the environment, and we'd end up with our acetal. Okay. The net result is that I've added that red OH and the blue hydrogen. Total, I'm adding water, so this was a hydrate. Yes, Jeff.
On the first step, didn't the negative OH just attack the carbon without having to take off the water?
We have hydroxide reacting with water to produce hydroxide. Did I have to have the hydroxide react with the water? No. Okay. Why did I show it happen? Because we're trying to address our nucleophile versus electrophile. So that's our key difference. Okay? And we now have the product out of this, our formal hydrate. Okay? And what did the textbook do? They had the hydroxide directly attack. Okay? So they simplified a step. We get the proton transfer and we get our answer. The question was brought up as I walked around that if we look at our product, I'm sorry, it's hanging off there, we have this dash for a hydrogen and we have a wedge for a hydrogen. Okay? Which would imply that we have a stereocenter. Is there a stereocenter? No. Why are we showing the wedge and the dash? Could we change the structure so that I would have a stereocenter? Yes. Okay. So they're drawing the wedge and dash on there not because there's a stereocenter, but trying to call attention to the chemistry of what's going on here. Okay. If we push this a bit further, look at how they drew it. The hydrogens were coming in and out of the plane. So let's go back to our starting structure and draw that structure again, where our hydrogens are coming in and out, right? And since it's roughly, sorry, let me draw that again. Roughly a planar structure. It's going to look a little bit weird because we have the wedge there, and then our hydrogen in back would be immediately behind it, right? Okay, and there's our oxygen. So we're just turning the structure on end. Why might we go ahead and do this? Is that what I drew actually our starting material? There's something missing? The pi bond. I didn't show the pi bond. Well, how do we make the pi bond? What orbitals are used in a pi bond? So really, I have p orbitals, and it is that p orbital overlap generating the pi bond, right? Everybody good with that? What is our nucleophile attacking?
Carbon.
What on the carbon is it attacking? What's that, Wyatt? The p orbital. Why is that relevant? It can attack from either side, meaning when we do this addition, there are two possible products that could come out of this. Okay? For this question, what is the relationship between those two possible attacks? They're the same thing. They're identical. Right? But what they're trying to set up with the showing that stereochemistry is get you to think about and realize that it's the p orbital that's getting involved in this. And there's two lobes to that p orbital, which means I get two possible reactions or two possible products out of this. Okay? Which we've seen already, because this was what type of reaction? A nucleophilic what? Addition. What do we say was the issue with addition reactions? You're reacting pi bonds, and pi bonds exist above and below. Every time we do an addition, we get two possible products. Okay? For future reference, and it has to be for future reference because I have no idea what they're actually called, the different faces of the carbonyl, or your p orbitals, are called something different depending on the attack. Both are equally valid, but they'll go through and say, well, the attack formed here, or the zip attack occurred here. Right? And again, I don't remember what those names are, but they'll reference the faces of the carbonyl like that. And it's just getting you to realize it is an addition. Additions will produce two products. Okay? Those two products could be identical to each other, as it is in this case. Make sense? So that was a 5-minute answer to a 2-second question. Make sense? We good? Okay. What could we do to make the electrophile more electrophilic? Okay, well, it's again recognizing where our pieces are. The electrophile is our carbonyl. That carbon needs to become more positive. Okay. To become more positive, what has to happen to it? If I make the overall structure more negative, that doesn't make an atom within that structure more positive. That makes the overall structure more negative, which then makes it more nucleophilic, not electrophilic. That carbon needs to become more positive. It's not technically the alpha carbon, which I think I heard you say. The alpha carbon would be where those hydrogens are. There isn't an alpha carbon here. Okay. That's the parent carbon, if you want to call it that. I don't know what its name is. The 0 carbon. Alpha is the next position. Okay. That carbon needs to become more positive. Well, to become more positive, what does it need to do? Lose a bond. It needs to lose electrons. Well, look at that structure. Where's the easiest bond for it to lose? The pi bond. So take those electrons and move them up to the oxygen. So if we just drew out a resonance, and this might be where you were going, Wyatt, we would have that formal positive on the carbon, but we have a formal negative on the oxygen. Okay? So yes, we see a negative charge in our structure. The carbon isn't any more or less positive now because they're resonance. How can I make the carbon actually more positive? Well, I better not have a negative charge anymore. If I can get rid of that negative, the carbon is now positive. How can I neutralize that negative? Add a hydrogen. Add H+. The result is that I would have OH, and I now have that carbocation. That carbocation is now significantly more reactive than the original electrophile because it's formally positive. Okay? Well, what type of reaction did I do there? I took a hydrogen that was free-floating and I attached it to my structure. Ugh, that's an ugly arrow. The hydrogen is, it's just a transfer of hydrogen, so it was an acid-base reaction. Okay? What did I add to it to make the electrophile more electrophilic? The acid. So by adding an acid, I make the reaction more electrophilic. Okay? We're moving into lots of acid-base dynamics, and it can mess with our ability to interpret charges. Right? So if we're under basic conditions, what charge would I expect to see in all my structures? A negative charge, because a base, hydroxide, is negative. If I'm in an acidic condition, what charge do I expect to see on all my structures? A positive, because acids add H+. So when you run under acidic conditions, draw out your mechanism to make sure you never see negative. Because under acidic conditions, it should always be positive. Okay? Kind of makes sense? We do run into some pseudo exceptions. Is the negative drawn here invalid for our mechanism? No. Why not? Where did that negative come from? Resonance, which means I'm oscillating back and forth between those structures regardless of what condition I'm under, acidic or basic. So resonance, it's okay to show charge. Right, that is fine. Just don't form an intermediate that is formally negative. Make sense? We drew out a full reaction here. Notice we end up with more steps. Why do we have more steps? At least is the official one. That first one that's our differentiator. Under acidic conditions, we activated the reaction to run. Under basic conditions, do we have to activate the reaction? Initially, I drew it out like that, and you're all like, well, why'd you do that? Couldn't the hydroxide have just directly attacked? Yeah. Under basic conditions, we already have our strong nucleophile. We can initiate right out of the gate. There's no activation. We're already there. Under acidic conditions, we have to do that activation step. That activation step adds a step to our overall reaction. Make sense? Okay. So if we scale this out onto energy diagrams, I just want you to see these. Our uncatalyzed, our very first step produced that Zwitter ion, that dually charged species with the negative and the positive. Okay? And unfortunately, they did this with alcohols. So let's make those waters real quickly. It's easy enough, right? Erasers. Lovely. We added water. Everybody see that? In our first structure, we have a positive and a negative. And the second one, under basic conditions, what happens? We still have a formal charge, but we only have one formal charge. Under acidic conditions, we have a different formal charge, but it's still only one formal charge. That one formal charge drops the energy of the intermediate, and we end up seeing a faster reaction occur because of it. The activation barrier drops. Why does it almost come out as an even energy? What's that? Not a bad idea. Our reactant energy is going to go up because we're starting with charge, and our product energy will go down because we're starting with one less charge. Okay? So that should even them out. It's not a bad idea. I like that. I swear I was thinking of something else. Oh, let's take a look at just the first one. Okay, we start with a pi bond, we end with single bond, sigma bonds. Shouldn't that be lower in energy? I lost a pi bond. Why does it go up in energy? Because we have the charges. So when we're looking at our reactions under the base and acid catalyzed, okay, we're starting with a pi bond, we're getting rid of that pi bond. It should kind of drop in energy. It doesn't go completely exothermic because there's charge there. Okay, so it does balance out roughly. Kind of makes sense? Okay, that was with water attacking. Okay, what was the part of water that was attacking? The lone pair on oxygen. So does it have to be water? Well, don't do that. Keep going back. Does it have to be water? No. Any oxygen with lone pair electrons and a hydrogen, so anything with an OH, is a valid species to use. So any alcohol, any R group does the exact same thing. Okay? And we can go through and scaffold through that single nucleophilic addition. Kind of make sense? Okay. What is the difference about adding an alcohol as opposed to water? I would argue it's probably the same speed. We aren't going to get much of a speed difference there because it's still an oxygen with lone pair electrons. The carbon versus hydrogen isn't enough of a difference. Okay, so let's make this middle one run with water. Okay, so just ignore the energy. We'd end up with OH, right? Everybody get that? And we'll make the last one run with the alcohol. Anybody see any differences yet? There's not carbon bonds. Let's push it all the way to the final end. We'd have OH, right? This one over there, we'd have that OH, we'd get rid of that. Wouldn't have that formal positive anymore. We have an ether, okay, the beginnings of an ether, sort of. Can't really call it an ether because one of the carbons is also an alcohol. So an alcohol and an ether next to each other is going to change the chemistry and get us a new functional group. Okay? When it was two alcohols next to each other, we called it a hydrate. This reaction started because we had an electrophile. Why was our carbon electrophilic? Why was it partially positive? Yes.
Because of the partial negative from the oxygen stealing.
The oxygen was stealing electrons from it, right? So we had a carbon that was pulling electrons away, or an oxygen pulling electrons away from a carbon. Okay? What do we have in our products? Did that carbon stop becoming positive? You're shaking your head no. Why?
Now there's another oxygen here and stealing electrons.
Okay.
It's bonded to it.
The slide actually has it colored in, right? The blue box. We started with a carbonyl electrophilic, and we look at that same blue box in our product. It's still connected to two oxygens. It still has two oxygen bonds. If anything, it is now more positive. Okay? If we compare across, can I tell a difference between those OHs? No, the only way I can tell a difference is because I colored them differently. But if I didn't color them differently, they're identical. Can I tell a difference between OH and that species? Yeah. Okay. With the hydrate, that's as far as I can see. Okay. I don't see any more chemistry with the hydrate. But with this other new functional group, I still have an electropositive carbon. That electropositive carbon could be attacked again and could cycle more chemistry to the point where I no longer have an OH, but I have another carbon chain. Okay. What we're looking at is that the activity of that carbon does not change when we go through this reaction with the nucleophilic addition. It is still electrophilic. Okay? And depending on the conditions we're under, we can continue to have it react. or it could stall out. Right? So if we actually push them being alcohols, guess what happens? It can, theoretically, completely exchange the oxygen on our carbonyl and replace them with the oxygens of alcohols. Okay. It's kind of, sort of color-coded, though it may not be obvious. The oxygen of our carbonyl is the oxygen of water that's been ejected from the structure. The oxygen from our alcohols are the ones connected to our electrophilic carbon. Okay. That is now a diether with one carbon being shared in between. Because the ethers are now inextricably linked, we have a new functional group name. That new functional group name is?
Acetal.
It's an acetal. Okay? Which ultimately comes back to its origin on where it came from. Okay? It was first noticed with aldehydes and acetaldehyde. So when acetaldehyde reacts with your alcohols, we can end up with this acetaldehyde kind of looking structure. Okay? So in this case, what is our nucleophile? It's still the alcohols. It's still that oxygen. Nothing's changed about it. It's still the nucleophile. Our electrophile? It's still our carbonyl carbon. What other questions do I have done? Which direction does the equilibrium favor? Ooh, that's a really hard question. Okay, this is heavily equilibrium dependent. And it's going to depend on the strength of the electrophile, the strength of the nucleophile, and everybody's favorite thing to consider, entropy. Okay? All of that stuff from 152 that you tried to block out comes crashing back in when we look at our acetals. Okay? Can we speed the reaction? Yeah, just like we did with the hydrate, we can do the exact same thing here. I can make the nucleophile more nucleophilic by doing what? I can add a base. What is that base going to do? Get rid of one of the hydrogens, giving it a negative charge. So I can run under basic conditions and try and see what happens. All right, what's the other thing I could do? Add an acid. What is the acid going to do? Protonate our carbonyl, putting it or establishing a more positive electrophile, and that would speed it up. Okay? And this is where this becomes fun. We're now looking at the varying stages all the way through. Okay? So if we start with our carbonyl and our two alcohols, we'll stop at a first intermediate that would be roughly what we did with our hydrate after 2 or 3 steps, depending on our mechanism, at what is known as a hemiacetal, halfway hemi to becoming an acetal. Because I still have that electrophilic carbon, another equivalent of alcohol can potentially react and take me all the way to the acetal. Suppose you're saying, well, geez, this looks like a really complicated chemistry that for the most part you're telling me just stays as the carbonyl. Anybody know a common place to find acetals? What is everybody writing on? Paper. What is paper made of? Cellulose. What is cellulose made of? Carbohydrates. What are carbohydrates? Acetals. Okay. So your entire carbohydrate section of biochemistry is acetals. Okay. So everything we address, that whole top-bottom aspect on how we form, guess what shows up in carbohydrates? And you need to be aware of that chemistry so that you can then predict what's going on with the carbohydrates. It's all acetal chemistry. Okay? Which gets us to our first. Let's go ahead and tweak the nucleophile. Let's use a strong nucleophile and see what happens. So what I want you to do is add the rest of your mechanistic step into this. There are a couple mechanism arrows here. Go through and get me from the carbonyl to the full acetal. You can bring in more of that OR minus, that's not a problem. Okay? But come up with a mechanism all the way through. You're able to draw that, right? Okay. We now have a negative oxygen. Do we want a negative oxygen? No, so we're going to have to neutralize that somehow. Okay. This is where, kind of arbitrarily, we have our alcohol floating around in solution. And a lot of students don't like throwing that in there. But where did we get the negative oxygen to begin with? Where did we get this species? It was starting from an alcohol. So to make that active nucleophile, we took an alcohol and we threw lithium metal in it, or sodium metal. That reacts to remove the hydrogen, and then it off-gas hydrogen gas, removing it from the solution, and what we'd be left with is the active nucleophile in an ethanol solution or in an alcoholic solution. So there is alcohol still present. I cannot, under any circumstances, say, well, whoops. Actually, I can say whoops a lot. I can't add H+. That is a horrible thing to add now because okay, I'm under basic conditions. I can't add a strong acid in there. Okay? So to go through and do this, I can now show that alcohol. I can have my negative react with that, and I would end up with my Hemiacetal. Okay? Hemiacetal is partway there. I now need to get my full formal acetal. How does that happen? Okay. This oxygen can still pull on that bond, yeah. Then what?
Well, it'll end up bleeding off because that carbon's electrophilic and both the oxygens around it.
So what you're saying is I end up with this.
Yeah, but the OR will attack that electrophilic carbon.
Okay, so that's a secondary step though, so that's what I want to be careful in. Okay. Should I be able to do this step first? Why not?
You're going to have to have something that forces it.
Why do I have to have something force that hydroxide off? I agree entirely.
Because it's still more stable with the oxygen, allowing it to share some of the electrons.
Kind of accept that.
Still basic.
I'm still under basic conditions, which means the charge of the structures I need to be seeing should be negative. I'm showing a positive that's already starting to be questionable. Okay? So it doesn't make sense to have that bond cleave because I'm showing a charge on a structure that shouldn't be there. Take it a step further, I have hydroxide as a leaving group. Yes, it's leaving into a solution that's roughly the same stability, but that doesn't make it the greatest. And even when we have hydroxide as a leaving group, there were other features that added to it. If you're thinking back to the lab, in the lab we had hydroxide leave, the resulting structure had lots of conjugation. The conjugation drops the energy overall, and we can see that reaction occur. We're not getting more conjugation by doing this. Okay? So that doesn't really work out for us. Okay? So instead, we have to have something force that off. Okay? So let's have another equivalent come in and attack. Well, now it's getting forced off by that negative charge. And now I would have my acetal. So I do have the hydroxide coming off, which isn't the greatest, but at least it's coming off into a similar environment. I'm also canceling a negative at the same time that I do this. So overall, not horrible. Would I expect that reaction to occur? So no. Now why? There's the easy answer that has already been answered by at least some people in the classroom. If we look at what was drawn on the slide, the arrows tell you no, that reaction's not going to happen. We've got equilibrium arrows all the way through this, except at the end, I'm not showing good equilibrium arrows. I'm saying it lies predominantly towards the hemiacetal. Okay? So that's the cop-out answer. Now you need a real answer. Why would I expect that to not occur? I'll give you two, and we already answered one of them.
We have stirred inverts.
Yeah.
What type of mechanism are we trying to show here for this step? An SN2. It's happening simultaneously. in a simultaneous substitution reaction, what do I want for my substrate? The least sterically hindered possible. Is that electrophilic carbon low steric hindrance? No. It is massively blocked by the methyl and the OR already there. Okay? So under SN2 conditions, this does not make sense. We can't run under SN1 because we're under basic conditions. So we're forced under SN2 conditions, which suggest I'm not making the acetal, which is indeed the case. We're running under SN2 conditions, bad leaving group, okay? Massive steric hindrance on the substrate. Typically, when we run under the strong nucleophile, we stop at the hemiacetal. It is too difficult sterically to continue forward to the acetal. So basic conditions, acetals don't form. Okay. Well, if acetals exist, what does that then mean? They do form under acidic conditions. Okay. So now what I'm going to ask you to do is to, oh, who's that coming in the door? Who is that over there? Who are they? Where are those people? Oh my gosh. Oh. Oh, I have no idea who they were. Did you say so stupid? That's not fair. If we run under acidic conditions, okay, the very first thing that happens is we have that strong acid. We need to neutralize the acid by reacting it with the carbonyl. Okay. We now have a stronger electrophile that can react with our alcohol through a nucleophilic addition. Okay. The result is we'd end up with our positively charged intermediate, which we can neutralize by having another equivalent of our alcohol act as a base to remove that hydrogen. Notice again that it's the alcohol acting as a base, not a strong base. It has to be a weak base through here. Okay? At the end of that, what do we have? Well, we'd have our hemiacetal. Okay? Now here's the part that I want you to do on your own. Because we've gotten to the hemiacetal before under multiple conditions. We even did it as a hydrate. What I want you to do is try and get the rest of the way from the hemiacetal to the full acetal under acidic conditions. Okay, remember, acidic conditions, the very first thing you need to do, get rid of the positive hydrogen. Okay, so take a switch, come through and react with that hydrogen. Okay, the oxygen from our OH, yeah, our alcohol, as opposed to the OR. Why would I have that one pick up the hydrogen and not the OR? Okay, it goes towards what we're trying to do. We're trying to get to the acetal. I don't want OH, I want OR. Okay, so I could just as easily have put the hydrogen on the OR, but if I had done that, I'm tracking backwards. Okay. I have a goal in mind with the acetal. I'm trying to do whatever it takes to get there. Okay? And yes, we may not be happy with that, but this is equilibrium. Equilibrium is going to look at each of those stages and say, well, I don't really like that step. Too bad, we're doing it. We'll come back and evaluate later whether or not that was going to work. Okay? So I put that hydrogen on the structure, and what I would end up with, well, too bad for not showing arrows, I'd have water attached to the structure. Well, water is a phenomenal leaving group. So great, oxygen says, hell yeah, I'm taking the electrons. Rips the electrons off, and we'd end up with a carbocation. Okay? If I had instead drawn something along these lines, so let's call red, would I have drawn an acceptable mechanism? Why not? I'd have a primary carbocation coming off. That's not allowed to form. Okay? So yeah, I can say water's a great leaving group, okay? But I'm not allowed to just accept water as a great leaving group. Okay? I need to be able to prove that the other species is allowed to form, is stable. Okay? So before I continue on with any mechanistic stuff, I have to evaluate that carbocation. What is special about that carbocation? I did a horrible job with this mechanistically because I didn't show it. There's a resonance stabilization of that structure. That's what allows that carbocation to form. Added on top of which, what have I now formed? Positive oxygen, true. Does oxygen want to be positive? No. So that bond that I just made, that pi bond, is dying to break open. That's awesome for the next step. What else is special about that? What functional group do I call an oxygen bound to a carbon with two bonds? A carbonyl. What started this whole reaction off? A carbonyl. I now have a carbonyl. What can that react with? Oh, a nucleophile. And it can be a weak nucleophile because that is a positive oxygen. So I can take a second equivalent of my alcohol and have that now attack. I would end up with the protonated form. I can remove that hydrogen, and I'd end up with my final structure of the acetal. Okay? Every step of that is now valid. The big difference for us is that last sequence. Why is that last sequence okay under these conditions, under acidic conditions, but then bad under basic? Well, in basic, what was our leaving group? Hydroxide. Was that good? No. What did this mechanism fix about that? It made it water, and water is a great leaving group. So the leaving group is better. Okay? Do we have to worry about steric hindrance? Why not? We're forming effectively a carbocation under under acidic conditions. We're effectively going through an SN1 mechanism. So I don't have to worry about the steric hindrance issue. Okay? So under acidic conditions, I can make it all the way to the acetal. Okay? And it is in equilibrium. And this is where we run into that issue of, well, does it want to do that? Want is all relative. Okay? Did you want to come to class today? Be honest. No. Why are you coming to class today? Well, you wanted a grade so that you can move on to some other class, and I just happen to be a gatekeeper. Okay, so you deal with me for 16 weeks before you can ignore me the rest of your life. That's cool. Okay? As long as we're all on the same page, we're fine. Okay? Same thing's happening here. Okay, we have kind of gatekeepers through this reaction. We're now stuck between carbonyls and acetals and trying to decide which way does it favor. And everything we've talked about just says this is how it can work. We haven't said how to make it work. Okay, and that is kind of the next thought. So when we look at carbonyls, not only should we be considering that it's an electrophilic carbonyl, but that if I have alcohols present, I can go through and form hemiacetals, and I can go through and form acetals. So I need to be able to look now for those two new functional groups. I have to look at a structure and say, that's a hemiacetal, that's a hidden carbonyl. Carbonyls have all this other chemistry accessible to them, if only I can unhide it. Or looking at a structure and saying, that's an acetal, that's a carbonyl. That allows me all this other chemistry as soon as I can get it out of that state. And because it's all reversible, it's now just a question of how do I change it. Okay, well, we've got some basics from 152 to be able to predict how to take a carbonyl and turn it into the acetal. How could I make the carbonyl an acetal? Test your 152 knowledge. I can add a ton of the alcohol. Okay? If I have a reaction that's in equilibrium, if I add a ton of one of those reagents, Le Chatelier forces that towards the acetal. That's going to force me this direction. But if I'm starting with the acetal and I'm trying to get the carbonyl, what can I do? I don't do the opposite.
Add to the opposite side of the equilibrium.
Add what to the opposite side?
Water, I'd assume.
Now I'll add a ton of water to force the reaction the other direction. Okay. What else could I do to form the acetal starting the carbonyl? No, if we balance out the carbonyl and the alcohol, we don't get an equilibrium shift. We just get a crap equilibrium. remove product. As we run the reaction, remove water from the reaction. That can help push the equilibrium. Thinking of the flip, if I want to get the carbonyl from the acetal, I can try and remove the alcohol as I run it. Okay? The problem with removing alcohol or water, their boiling points are very similar. They aren't easy to remove from the reaction at the same time with the carbonyl and the acetal. So they aren't the easiest things to remove. Typically what we're doing is forcing the reaction by adding either a ton of alcohol or a ton of water. Okay? So we know how to force it now. So when we look at a reaction, we go, oh, they're trying to make that carbonyl an acetal because they're saying they're using 50 billion equivalents of alcohol, right? Because every time we look at a chemical reaction, it says something about the concentration of all those species, right? I'm seeing a lot of people shaking their head right. Name a reaction that showed the concentration. You don't just shook your head, yeah, that it happens. Name a reaction that shows the concentration. Okay. 1. Okay, well that sucks. We don't show concentrations in our reactions. They aren't in our reactions. So when you're looking at a question and trying to decide how should it progress, should I be making acetal or should I be making the carbonyl, you have to be able to say there's a carbonyl and alcohol, they probably want the acetal, so I'm going to try that. Or look at a structure and see the acetal and they're adding water, they probably want you to go to the carbonyl. There isn't a concentration gradient in there for you to say, oh, that's clearly what they're trying to do. Okay? You have to, unfortunately, read between the lines and assume that whoever was doing the chemistry has scaffolded it appropriately. Okay? There are other tricks that we'll look at, but we aren't quite there yet. Okay? So, identify the following. Hydrate, hemiacetal, acetal, or none. I will give you 1, 2, 3, 4, 5, 10 seconds per sounds reasonable, 50 seconds. Go. $40 seconds. You got them? What's the first one? Next one. Ooh, look at that. Blue for water, like hydrate. Next one. Acetal. Next one. Last one. Right. So it looks like, or it sounds like you guys did most of those right except for that last one. Okay. To be in acetal, we are looking for a carbon that is bonded to 2 oxygens. Okay. Single carbon bonded to 2 oxygens. So when we move to the next one, we have a single carbon bonded to 2 oxygens. There's our acetal position. Okay. Even the hemiacetal, we're looking for a single carbon bonded to 2 oxygens. We still have that there. Why is the hemiacetal different from the acetal? One of the oxygens is an alcohol instead of an ether. How is the hydrate different? Because it's still a carbon connected to 2 oxygens. 2 alcohols. That last one? Sure, I've got a carbon bonded to an oxygen. I've got another carbon bonded to an oxygen. One of those carbons has to be bonded to another oxygen. Is it? No. So that position was an invalid position to be looking for in acetal. We can move to the other side. There's a carbon. There's a carbon. Are one of those carbons connected to a second oxygen? Nope. No acetal. Okay, makes sense? So, what's the next trick to this? Identify the carbonyl and the alcohol used. Sorry, I shouldn't laugh at that, but too many people like whimpering. Let's do it for the first one and the second. Identify the alcohol and the carbonyl used. So here we go. let's go ahead and take a look at those. So my hint was drawing them out really, really big. Okay? And really, the part that I was trying to draw really, really big was not the whole structure, but really what part? Just the bonds to the oxygen. The acetalic carbon, if you will, stays with 2 bonds to oxygen. It's just now a new oxygen, and it's a double bond. What happens to the other oxygens? They need to become alcohols. There's the answer to the first one. Okay. Let's do the exact same logic on the other one. We're going to erase through there. I need my double bond to my oxygen, hydrogen, hydrogen. That wasn't that bad. Come on. It's so much easier when you know the answer, right? Does everybody see it? Okay. The first one, admittedly, I think is significantly easier than the second one. The second one becomes really hard because on the exam you would never see your answer that way. 2, 3, 4, 5. You would probably see the answer written something like this. 2, 3, 4, 5. Carbon. 2, 3. You'd be like, well, I don't know how that could ever become an acetal. Okay. It can cycle back on itself. All of those are sigma bonds. We can freely rotate those, and it can cycle back. Between these 2 acetals, which one is the most stable? Left or right? As a hint, it's correct. It's the right one. Why is the right one more stable, right? Correct? Right. Why is the right one more stable?
Because it has a ring.
It's not just that it has a ring, it has a 6-membered ring. The 6-membered ring is a very stable structure that will cyclize back on itself. More than likely, if we tried to buy that aldehyde, it would cyclize and we'd have the cyclic structure. The one on the left, we've got 3 molecules. All of those independent pieces have to come together to stay bonded. Okay? And that becomes a lot more challenging. Okay? Yeah, I want to talk about this first, but then we can double back. Okay? So if we take a look at these reactions, where would we expect the equilibrium to be favored? Reactant or product? So that first one, reactant or product? Product. How do you know it's the product?
The arrows.
The arrows, yes. The arrows show you that the product should be favored. But of course, we'll get the question, why?
H2Os in the products. Pretty stable.
But H2O is pretty much just as stable as ethanol. If we run a pKa argument, the pKa's are almost identical. That's not going to help us out.
What's the entropy of the product?
Let's evaluate entropy. When we run a reaction with entropy, what are we concerned about? Do we want more things or less things for entropy? We want more things. Okay? If we think about how we just leave stuff out, they will fall apart into more pieces when left to their own devices. So if we run a reaction that is entropically favored, we would expect more pieces at the end, not less. If we take a look at that top reaction, what happened? It got less. That's not entropically favored then. So why would we favor the products? How do you speed a reaction? Adding an acid or a base, so again you're jumping to the end, but that's ultimately trying to do what to speed the reaction? To make a stronger electrophile or a stronger nucleophile. Why does that first one heavily favor the products? What can you tell me about that electrophile? It is probably the most electrophilic carbonyl that we have because those hydrogens can't stabilize with electrons that center carbon. Okay? So that, as far as our carbonyls that we're so far concerned about, aldehydes and ketones, is the most electrophilic. That's the reason why it's going to favor the products. Okay? We're starting with probably the most electrophilic species we can get. Okay? How about the second one? Which way was favored? Reactants. Why? Okay. We can go back and take a look at our starting electrophile. Really the only difference between the first and the second is the electrophile. The electrophile now has 2 carbons. We're looking at a ketone versus, it's formaldehyde, but effectively a double aldehyde. Okay. Those methyl groups stabilize that carbonyl carbon, making it less susceptible to the nucleophilic attack. We could run it as a steric argument. We can also run it as an electronic argument. Okay? Both things are saying that reaction doesn't go. What does our entropy say?
There's more pieces on the
There's more pieces on the reactant. We get a favoring for the reactants. Okay? The top one overcomes our entropic effects just because it is that much more reactive as an electrophile. The bottom one, which side of the reaction is favored? Hint, they aren't showing equilibrium arrows. Products. Okay. Why might we expect the products to be favored? We have a 5-membered ring in our final product, which is more stable. Okay? Do we have the entropic effect preventing it from occurring? We start with 2 things, we end with 2 things. So because of that ring structure, we've stabilized that acetal, and we increase the likelihood of forming it. When we're forming our acetals, the primary driver for almost all acetal reactions is ring structures. Okay? The ring structure is what's going to be your acetal. Okay? That's how they show up. We rarely see them in any other form. It's really just the ring. Okay? So I do apologize because I talked too long. As per usual, what I'll leave you on is identify the alcohol and the carbonyl for these 2 structures. That's what we'll start Wednesday with, and I'll make it a quiz because I'm suspicious nobody's actually doing these things. And actually, we're going to do it differently. I'm going to give you a quiz paper,